Okay, this is the rock, paper, scissors activity, which is the next thing that's listed. And you should attempt to do this. You can play it with someone in your family or friend, whatever you want. Hopefully everyone knows how to play rock, paper, scissors. If you don't, there are instructions right here at the beginning of the activity. These are posted in Momentum also, right underneath the 5.1 notes. So you just decide who's going to be a player and you play a game. So I played with the computer and these are my results. So R stands for rock, P stands for paper, S stands for scissors. And in the results, T stands for a tie, A stands for player A1, and B stands for player B1. And you can see we did this 20 times. So, I know we haven't really discussed probabilities yet, but this is sort of a feel your way into it kind of activity. I did give you a hint right here that says that, the probability is the number of times a certain outcome happened divided by the total number of rounds. So, for example, based on this game I just played, what's the probability that player A won? Well, let's count how many times player A won. So I see 1, 2, 3, 4, 5, 6, 7. I see player A won 7 times out of 20 trials. So in this case, the probability is 7 over 20. And if we round that to 3 decimal places, sorry, in this case, those little squiggles I drew originally mean approximately, but this is an exact answer. So 0.35. Okay, what about the probability player B won? Well, let's go see how many times player B won in my little game here. 1, 2, 3, 4. Looks like player B won 4 times out of 20, which is 0.2 when we round to 3 decimal places. Now let's do the probability of a tie. So we count the number of ties. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we had 9 ties out of 20 games. So if we put that in the calculator, we get 0.45. And for those of you who are not sure how to put a fraction in the calculator to get a decimal, let me pull up my little calculator here, make it bigger. I wish I could make the actual calculator bigger. But what we're going to do, first I'm going to hit clear. So if you need to type a fraction to get a decimal, you just type the numerator, the number on top, divided by the denominator into your calculator. So 7 over 20, and that gives us 0.35. So that's how I got those numbers, in case you're wondering. Okay. So now, if we just play one round of rock, paper, scissors, what happens? Okay, player 1 does something and player 2 does something. So let's start with player 1. player 1 could either make a rock, make paper, or make scissors. And then player 2 can also make rock, paper, or scissors. And that's true regardless of what the first player does, right? So let's go ahead and list our sample space. So I did a tree diagram. So our sample space is rock, 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 paper, rock, scissors, paper, rock, paper, 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 scissors, or scissors, rock, scissors, paper, scissors, scissors. So that is our sample space. So how many total possible outcomes are there? Well, we just count the things that are separated by commas. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 total outcomes in the sample space. Okay, moving on. How many ways can player A win? Well, player A wins if it's rock, scissors. So let's just write this over here. Player A wins if it's rock, scissors, because rock breaks scissors. Player A wins if it's paper, rock, because paper covers rock. And player A wins if it's scissors, paper, because scissors cut paper. So out of those 9 ways of the total possible outcomes, player A can win 3 out of 9 times, which is approximately 0.333 if we round to 3 decimal places. Okay, player B wins if, let's see, scissors, rock, because remember the second one's player B. So rock beats scissors. Paper beats rock. And scissors beat paper. So player B can also win 3 out of 9 ways, which is also 0.333 rounded to 3 decimal places. And how many ways can they tie? Well, they tie if they get the same thing. So that's either rock, rock, scissors, scissors, or paper, paper. So there's 3 ways they can tie out of 9 total ways. So that's another 0.333 when rounded to 3 decimal places. And I'm sorry, we've done this wrong. So take these 3 and switch them with these 3. In other words, I should have just put the number of ways, which is 3 ways to win, in 3, 4, and 5, and those probabilities should have been in 6, 7, and 8. I'm not going to remake the video, though. So hopefully that makes a little bit of sense. So now we've calculated the probabilities 2 different ways. We calculated it once by playing a game, And we calculated it once by looking at the sample space and all the possible outcomes. So, were the probabilities for player A winning in part C? So in part C, we had 7 out of 20. And in part D, the probability that A wins is 3 out of 9. For mine. Now, where you played could be different. So in my case, were the probabilities different? Yes. So why do you think they were different? Or if yours happened to be the same, why do you think that is? So here's really what we just learned by doing this. So part C was an experiment. And part D was what we call classical probability. And this is where the law of large numbers comes in. So for part C, we got player A wins and remember, this is my numbers, not you. 0.35 of the time. Part D said player A wins 0.333 of the time. So that's pretty close, right? 0.333 to 0.35. But it's not exactly the same. So the reason that that happens is because in an experiment, anything can happen. So let's think back to flipping a coin. If you flipped a coin 100 times, you would expect 50 of them to land on heads. However, because actually doing an experiment means we're subjected to the real world and crazy things can happen, it is entirely possible that we could flip a coin 100 times and get 100 heads. So that's what we need to know here, is the difference between experimental and classical probabilities. Now, for number 3, do you think the probability calculated for player A winning in part C, so in our experiment, would be closer to or farther away from the probability of player A winning in part D, which is our classical probability, if you played 200 rounds instead of 20? And your answer should be that yes, we would expect it to be closer. To be closer based on the law of large numbers. So that's it for this. We will pick up with the rest of section 5.1 in another video.